Okay, hello. How are you doing? Hope doing very well and ready for the next quiz. The last quiz that we're going to have, quiz number 4 before the final. So we are going to continue studying power series. So I give you the property of the power series. We look at it as a function. So show that this function can be differentiable, can be integrable, and then we use it to be able to produce more power series. So what we're going to do, we are going to get into the, if you want to prove that a function would have a power series, there is another method to do it. This method would form the special series that we're going to call a Taylor series. A Taylor series is going to be a kind of power series, but it would be involve more methods of finding the, the power series of the given function. So we're going to introduce the Taylor series that will help us to be able to get the power series of the famous function like a trigonometric function, exponential function. We haven't given you any example of the sine x, cosine x, and then you realize that all the nice functions in calculus, they are nice because you can write them as a power series. Okay, so that's going to be the idea. So you've got to be patient. We are going to talk about the theorem. But in fact, when we want to do it, we try to use some shortcuts. So I give you that one too. Okay, so this would be 11.10 for the Taylor series. So let's get to my notebook. Give you the idea of the Taylor series. So this is the one that we did. Okay, the last thing that we did, we introduced differentiability, integrability of the power series, and we were able to produce more power series of a famous functions. So this is going to be officially, this is 11.10. Okay, 11.10, and we are going to talk about Taylor series. Taylor is a famous English mathematician. Taylor series. That's it. So I can define the Taylor series right away, but I will give you some motivations of how we arrive at this definition. So let's start with the power series, which is defined by a function. We did this type of ideas the other day. So suppose we have the f of x is a function that's represented by a power series. The power series like Cn times x minus a to the n from 0 to infinity. Suppose this series, you know that this series is going to be convergent, and we have a radius of convergence. Now we are going to investigate this one a little bit more closely, if you like. Then let's expand it. If we expand it, so the function is going to be f of x equal to, first one you start with the n equal to 0, so that gives c0. Anything to the power 0 would be 1, so the first term would be constant term c0. If you replace the n by 1, c1 x minus a, so it's going to be c1 times x minus a. And if you replace n by 2, so that gives you c2 x minus a squared, and continue. I write one more, and that's going to be c3 x minus a to the third, and then you keep going. So that's going to be a representation of this function. Now, suppose you want to find f of a. Replace x by a. What's going to be f of a? You see f of a, the value of the function at a, and the a is the center of the series. You see, replaced by a minus a would be 0, a minus a would be 0. All these terms would be 0, except the first one, c0. So that gives c0. Okay, so c0 would be f of a. So this means if I have the function f, I find f of a, and that give me the first coefficients of the power series. So that's going to be the one. Now let's go back to this f of x here and differentiate it. We already talked about it. The power series is differentiable. So if you differentiate it, that give f prime of x. That would be f prime of x, okay? Then the derivative of a c0 would be 0. So that would disappear because that's a constant number. Over here, derivative of x minus a would be 1 because derivative of x is 1. So your first term this time would be c1 plus this one over here. Use the derivative of x minus a to the second power. You bring the power down. So that gives us 2c2. 2c2 times x minus a. And over here, you bring the c down. So that gives you plus 3c3. 3c3 x minus a squared. And everything else. Okay, so that's a derivative. Now let's replace the x by a again. If we replace x by a, that gives you f prime of a. Okay, that would be f prime of a. And over here, you see, everything else other than the c1, everything else would be 0. Because we replace x by a, that gives a minus a0, a minus a0. So that gives me the c1. Okay, that would be the c1. So if I have the function f, I want to find the coefficient c1, I just differentiate it and substitute get the a. Okay, let's go on one more step to see what's going on. Differentiate this one again. If you differentiate the f prime, you arrive at the f double prime. F double prime of x. So derivative of c1 would be 0. Derivative of this, you see, derivative of x minus a is 1. So your first term would be 2c2. 2c2 plus, now the next term, you see, you bring the 2 down, 2 times 3, 6. 2 times 3, 6. Okay, that gives 6 c3. That gives 6 c3 times x minus a. And you just continue with the others. Now, if you again replace x by a, so that f prime of a would be, you see, you get only the first term, which is going to be 2c2 here. Okay, that gives only 2c2. 2c2, everything else would be 0 again. Everything else would be 0 because you have x minus a, x minus a, x minus a. So from here, we can find the c2. So the c2 is going to be equal to the f double prime of a divided by 2. We can change the 2 into the 2 factorial, both of them are going to be the same. But we want to get the idea of what's going on with the formula. So this is the second coefficient. So the second coefficient would be f double prime, second derivative over 2 factorial. So the first coefficient is going to be f prime of a, you see 1 prime, 2 double prime, c0, no prime. Now, if you continue, if you differentiate it again, just once more, if you differentiate this one, that gives you the third derivative, okay? The third derivative of x is going to be equal to, so this would be 0. So the next coefficient that we're going to have is going to be 6c3. 6c3. Everything else would be 0 because of the x minus a. Okay, 6c3, and if you substitute the a, so that gives you 6c3. And then if you find the c3, you see the c3 would be the third derivative. The third derivative of the a at f at a divided by 6. 6 is 2 times 3, and the 2 times 3 is 3 factorial. So that gives you a, and that gives you 3 factorial. So that gives an idea of what is going to be going on and what's going to be the general term. So that gives you f there, the third derivative, divided by 3 factorial. See? 3 factorial the third derivative, second 2 factorial second derivative, 1 first derivative. So in general, if you continue this operation, you arrive at the fact that the derivative, you see the coefficient Cn is going to be equal to, you see, the end derivative. So the end derivative is the way we write it down, of f at a divided by n factorial. N factorial when this n can be 0, 1, 2, 3, etc. You see that give you. So what we did, we just find a formula for the coefficient of the power series that we did have. Remember, we start with this f of x. You see that was f of x, and that's a Cn that we find. So if we go back, if you rewrite that series, so therefore this is what you are going to have. So f of x is equal to, you see f of x was equal to what? C0. So it's going to be C0. And what is the C0? C0 is f of a. So that gives f of a plus C1. What is the C1? C1 is f prime of a. So that gives f prime of a times x minus a plus C2. What is the C2? C2 is the second derivative, you see. C2, that is going to be your C2. So the C2 would be f double prime of a over 2 factorial times x minus a squared. And then you continue. The general term of your series is going to be f derivative, n derivative, a over n factorial, x minus a to the n, etc. So in short, this is going to be the series sigma of, you see sigma of the nth derivative of f at a over n factorial, x minus a to the n from 0 to infinity. This series is going to be called the Taylor series. Okay, so if you're in this case, I just call it the function f of x. Okay, I call it the function f of x. So in general, if a function would be given to you, okay, so we are going to make it something general. Okay, so in this case, the function was given to you, we just get this series. Now, suppose we have a function whose derivative of all the orders means f prime, double prime. You see, that's going to be definition of the Taylor series in general. Okay, that gives us an idea. This is how we do the mathematics. We find out something, then we are going to make something out of it. So in general, if a function f, then f prime, okay, you can say that if let's say functions, if functions f prime, f double prime, all the derivative, that get the end derivative of the function, etc. If this function is differentiable forever, so this means we can find the first derivative, the second one, the third one, the fifth one, etc. If these functions are defined, means R exists, okay, are defined, going to be defined at a number, okay, at the number a. If this is going to be the case, then this series, you see, sigma of, that's in condensed form, n derivative of the f at a divided by n factorial times x minus a to the n from 0 to infinity. You see, that's one. You can expand it if you like. The first terms would be f of a. The second term would be f prime of a times x minus a. Okay, the next term is going to be f double prime at a over 2 factorial, x minus a squared, etc. And this is going to be called the Taylor series. It's called, okay, it's going to be called the Taylor series. The Taylor, it's going to be Taylor series of the function f at the number a. Okay, so you must know the definition of the Taylor series. A function would be given to you, and they ask you to find the Taylor series. So you have to find f of a, f prime of a, f double prime of a. Sometimes, if you find a couple of these derivatives, you may find out that there is a general pattern, and sometimes you may not. So sometimes you may be asked to find the first 4 terms of the Taylor series. So you go and find, up to the third derivative. So they give you the instruction to be able to do it. So that would be the Taylor series. The Taylor series. There is a special case of this series, which is much more popular. If if this a is 0, if a is going to be equal to the 0, then you get only power of the x. If this is going to be the case, then you see your series would be of this form: sigma of the n derivative at 0 over n factorial x to the n. So the first term is going to be f of 0. The second term would be f prime of 0 times x. The third term would be f double prime of 0 over 2 factorial x squared, etc. This is going to be called Maclaurin series. You must know the name. It's called, it's called the Maclaurin. That's a name. Okay, it's a Scottish name. Maclaurin. Okay, Maclaurin and the Maclaurin series. Okay, Colin Maclaurin, that's his name. So if this is going to be 0, it's called the Maclaurin series of the function f, of the function f. It's quite interesting that Taylor was English mathematician and Maclaurin was Scottish. Maclaurin is very popular. Okay, he used to be a very good teacher, and he's the one that for the first time he has written the calculus book for the high schools in Britain, okay, and mostly in Scotland, and even his books are teaching even today. He was very much interested in the application case, so he has done quite a lot in mathematics for engineers. And he was very famous, and he works with Isaac Newton, and there are lots of stories about him. Okay, so the Maclaurin series is easier to handle, and so if we write the Taylor series when a is equal to 0, that would be a shorter series. Okay, but each series would have its own advantage. Okay, so you have to be able to write down this series, and a couple of them to be make sure memorize them if you like. Especially it would enable us to find the exponential function. You see power series these are all power series. Okay, so this is another way to find the power series. I did the other day just using the geometric series, but there are some that nothing to do with the geometric series, and we can use the idea of the Maclaurin series. And they are going to be exponential functions. So we just give you example. This is it. I'm going to give you this example. You can memorize it and use it anywhere you like. So what we would like you to do is we'd like to find the Maclaurin series. Okay, Maclaurin series of each function. So the first famous function, of course, is e to the x, very popular. That's easy to find. You see, in order to find it, you have to find the value of the function at 0, value of the derivative of function f prime, f double prime. You see, this is your term. So you have to find the f of 0, f prime of 0, f double prime of 0. We just try a couple of them. In the case of the e to the x, it's easy. You know that because derivatives never changed. So that's it. You see f prime of x is e to the x. You know that second derivative again would be e to the x. Just going on forever. So even the end derivative of this function would be e to the x, never change. So if you find it at 1, at 0, sorry. So f prime of 0 would be e to the 0, which is 1. And everything else would be 1. Okay, so all the coefficient of your series would be 1. So the Maclaurin series that you want to write, you see this is Maclaurin series and 0 n factorial x to the n from 0 to infinity. You know that this is going to be officially is f of 0, f prime of 0 times x. Okay, f double prime of 0 divided by 2 factorial times x squared, and you continue. In the case of the e to the x, this is the way we write it down. We say e to the x is approximately f of 0 is 1. Okay, then f prime of 0 is 1, so that gives x. The next one is 1, so that gives you x squared over 2 factorial. Okay, then we get the next one is going to be x to the third 3 factorial, and you continue. You see the general term would be x to the n over n factorial forever. So that gives you e to the x. Okay, so what we can do is this is going to be a power series. You can use the ratio test. Okay, so one can use a ratio test to show that this series is convergent forever. We did it before to show that the series, the power series, this power series converges. And so you know that when it converges, the limit of the general term would be 0. So this is going to be useful. You can use it anytime you like. You see limit of x to the n over n factorial. When it goes to infinity, this would be 0. And then we can use this one to show that. Okay, any question? Let's look at this one. And we can use this one to prove that. Okay, so one can prove, this is a theorem, I'm not going to prove it. So one can prove that the power series converges to the e to the x, in fact. That the series converges to e to the x. And so you have this formula. You can use it anytime you like, except that. You see e to the x is equal to 1 plus x plus x squared over 2 factorial, x to the third over 3 factorial, going on forever. So the general term would be xn over n factorial. And the radius of convergence is going to be infinity. So this is going to be true for all, okay, for all x. Very useful. You can use it anytime you like. There are other ways to prove that, you know, that the power series of e to the x is this one, but this is the easiest one. Okay, so this is the first one. If you use it anytime, we accept it. I'm going to get 2 more for you. And then we can, you know, the problem that is going to be given to you is find the power series for e to the 2x. So you have e to the x, you replace the x by 2. Okay, so that's going to be the first one. Memorize this one. You can use it anytime you like. You see, this is the way your calculator would solve the problem for you. So for example, if you want to find e to the fifth, you know that you click on your calculator, you get it. The calculator, you see this power series is inside your calculator. So the calculator would estimate this sum for you. Okay, if you want to do it yourself, you may write just a couple of terms, but your calculator can write infinitely many terms. Okay, that's why you get it, right away with your calculator. It's going to be the same for the other functions. Okay, so that's going to be the first one. And we are going to do another function. Another function, of course, is the sine function. These are the one that we were not able to do it with using the other methods that we did. Okay, so same thing for this one. So again, f of 0. Okay, f of 0 would be the sine of the 0, which is 0. So that's the first term. You have to find the f prime of 0. So f prime of x. If that the sine would be cosine of x. So f prime of 0 would be cosine of 0. And the cosine of 0 is 1. So that's f prime. So write a couple of more. F double prime of x would be negative sine. And the f double prime of 0, it would be minus negative sine of the 0, which is 0. So double prime would be 0, just get one more. So if you find the third derivative, so you differentiate this one, that gives you negative cosine x. And if you substitute f double prime of 0, f tiers we call it, 3 times, it's going to be negative cosine of the 0, which is a negative 1. Look at this one, the first one is 1. The third one is negative 1. And the second one is 0. If you do one more, then you understand what's going on. You see the fourth one. If you have a negative cosine, would be negative sine, so this would be sine. So if you find it at 0, that gives you a sine of the 0, which is 0. You see, for the even order, second, the third, you get the 0. By the odd one, we get 1, negative 1, 1, negative 1. I can do one more for you so that you can see it. You see the fifth, that gives you cosine of x. So the fifth at 0, that gives you cosine of 0, which is 1. See, 1, negative 1, 1, negative 1. So in general, if you like a formula, in general, if you want to find the fn at 0, depends. Okay, depends which order do you have. If the order is even, you see if n is even, is equal to the 2k is even, this coefficient is 0 because you get the 2, 4. But if it's going to be odd, you see if it's going to be 2k minus 1 is odd number, means the first, the third, the fifth, as you can see, is either 1 or negative 1. So it's going to be negative 1 to the n. Because if you put, okay, n equal to 1, so that give you the 1, okay, the first one, you get a 1, negative 1, 1, negative 1. Okay, we start with n equal to the 0. Then when we get n equal to the 0, this is going to be 1. And then you continue for the other one. Okay, so we have a formula for you. So the conclusion is going to be, so what is going to be that we start with the sine x. So sine x for the time being is going to be almost like its Taylor series. So the Taylor series is going to be n derivative at 0 over n factorial x to the n from 0 to infinity. Okay, so your first term is going to be f of 0. The second one, f prime of 0 times x, f double prime of 0 over 2 factorial, x squared. Okay, I write one more. The third derivative at 0 over 3 factorial, x cubed, etc. Now, if you substitute, you see, if you substitute over here, the first term, f of 0, is going to be 0. F of 1 is 1. So for the even power, we get the 0. So this is going to be equal to, this would disappear. F prime of 0, you see it's going to be 0. That is 1. 1 times x would be x. And this would be 0 because the even power. Okay, this one over here is going to be, okay, the third one, derivative is a negative. So that's going to be negative x cubed over 3 factorial. And the next one is going to be 0 and then continue. So basically, this is going to be the Taylor series of the sign. Taylor series of the sign would be x minus x cubed over 3 factorial, x to the 5th. It's going to be alternating series. 5 factorial. There is no even power. No even power. So that gives x to the 7 over 7 factorial, etc. Okay, again, it can be proved that the convergence, it can be proved that the power series, because that's an estimate to start with. Power series converges to sine x. So you have the second formula that you have to memorize and you can use it anytime. So this is how your calculator would operate for the sine for you. Sine x is equal to x minus odd power x cubed over 3 factorial plus x to the 5th over 5 factorial. Okay, you just keep going. So if you want to write the general term, you are going to have a negative 1 to the n x to the 2n minus 1 over, okay, 2n minus 1 factorial. So just check to make sure you get it right. If you replace n by 0, you should get the first one. So you change it to the 2n plus 1. That makes sense. Now when you replace the n by 0, that gives you x. Replace n by 1, that gives you the third. And this would be negative. If you replace by 2, that going to be 4 or 5 over 5 factorial, etc. Okay, so I write it down again in condensed form. So if you want to write in the sigma form, sometimes you have to. So this is what you have. You have the Maclaurin series, or just the power series of the sine is sigma of negative 1 to the n x to the 2n plus 1 odd power divided by 2n plus 1 factorial n from 0 to infinity. Okay, which is going to be, as I told you, it's going to be x minus x to the 3rd over 3 factorial, x to the 5th over 5 factorial, etc. And this is true for all x, all values of x, which is very good. So this means if you want to change it to the sine of 2x, you just replace the x by 2x. Sine of the 5x, you replace by 5x. So that would be very useful to get this famous, okay. This, for the first one, it was proved by a mathematician from India. But in the history of calculus, later on it was done by Newton. It's like Newton or Newton. But most of the people, they say, no, it was done by Newton, but it was first done by a mathematician from India. Now what we can do, remember, the power series are differentiable. If you differentiate both sides, that gives you the series for the cosine, okay? Differentiate both sides. If you differentiate it, so by differentiation of power series, You get this one free. That's it. You get a cosine of x is equal to, you see the derivative of x would be 1. So that gives you 1 minus, that gives you 3x squared over 3 factorial. 3 factorial would be cancelled out. So you get even power this time. You get x squared over 2 factorial plus x to the 4th over 4 factorial. Okay, over factorial and minus x to the 6 over 6 factorial, etc. So that would be Taylor series or the Maclaurin series of the cosine. Okay, you can write down in the condensed form if you like. It's going to be sigma of. It's going to be useful to know both of them. So it's going to be sigma of -1 to the n again, even power x to the 2n over 2n factorial. And start from 0 to infinity. If we replace n by 0, x to the 0 would be 1. If we replace n by 1, this would be -1. That gives you x squared, and the top would be 2 factorial. If we replace n by 2, this would be positive. That gives you 2 times 2, 4, x to the 4, 4 factorial, etc. Okay, so you must know these 3, and you can solve many problems using using only these 3 famous. These are the good one. It's not the case that always if you find the Taylor series would converge with the Weyl function. But it's nice to know this, okay, and you can use it anytime you like. Okay, so there is so we can sometimes you may be asked to write the Taylor series of some other functions, so we can use this one. For the long time it was supposed that like the sine and the cosine, if you find the Taylor series of any function, that function would be Taylor series would converge to the function. But there is one example that give you otherwise. Okay, so it's not the case that anytime you just find the Taylor series, that Taylor series would converge to the function. There are some exceptional ones, but you can use this idea that I gave you over here, and you can go to and read your book if you want more information. But this is how we're going to use it to solve more problems. Okay, so make sure you memorize these 3 together. Okay, so this is how we're going to use it to get this number. So example is going to be, would like you to find the Maclaurin series of the following function. Okay, so find the Maclaurin series, call it Maclaurin series for each function. Again, we are going to use some 3 because if you want to differentiate, it takes time. The one that I gave you, you see the derivative was easy. If it's not going to be easy, I'm going to give an example, you see it. You may be asked, to just find a couple of terms. 4 terms, 5 terms, this is the way it's going to be given to you. So let's first do the nice one. So there you are. Just give you an idea. You need practice to get the tools running. Okay, this is the first one. F of x equal to e to the 5x. Okay, so what you're going to do is you go with the e to the x first, because e to the x is easy and we accept it. And then you change the x into the 5x. That's it. Don't try to find the derivatives. Okay, it can be done by the derivatives, direct derivative. It takes time. So we accept it. You say that, oh, note that what I have or what I know. What I know is it's e to the x. I know that e to the x is 1 plus x plus It's a couple of terms, x squared over 2 factorial, x to the third 3 factorial, and the general term, you can write down in sigma form if you like. General term is going to be x to the n over n factorial. That is e to the x. So what you want? You want e to the 5x. So replace x by 5x. So if you replace it, what's going to be the result? This is going to be e to the 5x is equal to the 1 plus 5x plus 5x squared over 2 factorial plus 5x to the third over 3 factorial. Okay, and the general term is going to be 5x to the n over n factorial. You have to simplify it to give us, you see, the power series is powers of the x. Some people, they leave it here. No, you can't. You have to continue. You continue, you say this is going to be 1 plus 5x plus, you raise this one, 5 squared or 25 if you like. So that gives you 5 squared x squared over 2 factorial. See? Then the next one is going to be 5 to the third, x to the third over 3 factorial. So the general one would be 5 to the n, x to the n over n factorial. That is now acceptable. Okay, so that would be a power series of, you don't have to simplify 5 squared, 5 to the third, etc. You write it down as is. If you want to write it in sigma form, you see e to the 5x is simply equal to the sigma of the general term. 5 to the n, x to the n over n factorial, n from 0 to infinity. This is true for all values of x. And then you're done. You see, this is how we do it, you see, nice. Because we already got e to the x, you see, that's what. You already got e to the x, so you just replace x by 5x because there is no restriction here. It can be done for all x. Since it's for all x means the radius of convergence is infinity. So that's why you can, can build up your series from here. Okay, so this is one. Give you more to get the idea. The next one, g of x equal to x times e to the x, you see. Again, if you want to go with the derivative, you have to use the product rule and getting complicated. You don't need it. You know e to the x. E to the x is can be written as the powers of the x. And this is x, if you multiply them together, because the power series of a function, you see, is unique. There is only one. There is only one that's going to be, you see, that the powers of the x that would be converges to the e to the 5x. So if you know a method to find one of them, you see this is one. Since there is not going to be a second one, so automatically this would be the power series of your function. It's going to be the same thing for this, okay? So the solution is going to be, you are going to start with this is it, you start with the e to the x. Again, e to the x is 1 plus x squared over 2 factorial, x to the third over 3 factorial, general term, you have to give us a general term, x to the n over n factorial, etc. What do you want? X times it by x. Times by x. What's going to be times by x mean? See, x times by e to the x. And the same thing here. It's going to be equal to the x times whatever we have. So we can do it right away. I just explain it. X squared over 2 factorial, the general term, x to the n over n factorial. So multiply. So what do you have? It's going to be x e to the x equal to x times 1 x times x squared plus x times x squared would be x to the third. That gives you x to the third over 2 factorial. The general term plus x. You see x times x to the n would be x to the n plus 1 divided by n factorial, etc. That's it. See, the term to the right is the power series, and it's already converges to the x e to the x. So this is d power series, d Maclaurin series, because you cannot have two at the same time. You cannot have two at the same time, so you are done. Okay, so that's the advantage of that three formulas that I gave you. Okay, so give you another one. Okay, so the next one is going to be something like, you see, f of x equal to, let's say, x squared cosine of the 2x. Again, if you want to differentiate, find it, it takes so much time to do it. So what we're going to do, we know the cosine. So you start with the cosine of the x, then replace the x by 2x to make it cosine of the 2x. Then at the end, you multiply by x squared. Okay, just be patient, do it step by step. So that's it. So yeah, you are going to note that you have to know the cosine. So you note that the cosine of x is equal to, the cosine is even power 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And the general term, you must know the general term, negative 1 to the n, x to the 2n over 2n factorial. That's a power series or Maclaurin series of the cosine of x. But you need cosine of 2x. So replace, okay, replace x by 2x. So what do you have now? Cosine of the 2x is equal to the 1 minus 2x squared over 2 factorial, 2x to the 4th over 4 factorial. You better focus on the general term. You see negative 1 to the n. That gives you 2x to the 2n over 2n factorial. Okay, and you can write on the sigma form if you like. So you have to, these coefficients, you have to pull them out. So you have to rewrite this one as, carefully, cosine of the 2x is going to be equal to, the first one would be 1 minus. So you pull out these two out, so that gives you 2 squared, x squared over 2 factorial. The next one is going to be 2 to the 4th. Okay, x to the 4th over 4 factorial, or just the general term. What is the general term? It's a negative 1 to the n, 2 to the 2n, x to the 2n over 2n factorial. See, this is the cosine of the 2x. Okay, but what do you want? You want x squared times. So times it by x squared. Times both sides by x squared. I write it on the sigma form so that you can see. If you want to make it brief, that's possible for you. You see, this is how you make it briefly. Okay, so the brief one is going to be, you see, that's a cosine of the 2x, sigma of n from 0 to infinity. Remember that was a negative 1 to the n. You did have x to the 2n, so you replace the x by 2x, you see, 2x to the 2n over 2n factorial. See, that's much easier. And we just bring that 2 down. It's going to be negative 1 to the n, 2 to the 2n, x to the 2n divided by the 2n factorial. That's easier. Okay, now you multiply by x squared. You see, x squared cosine of the 2x is going to be equal to the sigma of n from 0 to infinity. You see, that x squared, you just put it up here. because you multiply by x only, so that gives negative 1 to the n. Okay, 2 to the 2n, and you have x to the 2n. Then you multiply by x squared, x squared. Everything else stayed the same. 2n factorial. Now x to the 2n, x squared, you have the same base, you add the powers together. So the final answer would be x squared cosine of the 2x is equal to sigma of n from 0 to infinity, the top, negative 1 to the n, 2 to the 2n, x to the 2n plus 2. See, that's a 2n divided by 2n factorial. You see, that's a condensed form, the sigma form. It's much easier. Okay, but sometimes you may be interested to see what's going to be a couple of the first term. You can break it, and then you can do this, the same thing here. If we replace n by 0, so that give you the first term. In this case, it's going to be x squared. Okay, the first term would be x squared. If you want to find the second term, you see, I'll show you. So you don't have to bet. If you replace n by 0, you see, that would be 1, 1, 1. That gives you x squared only. So the top would be x squared. If we replace n by 1, so negative 1, the sign would be negative. Okay, the top, replace n by 1, 2 squared would be 4. 4. X to the, you see, x to the, replace n by 1, that gives x to the 4th. Okay, and divided by 2 factorial, because n equal to 1. So that gives you 1. We want to find the next one. If you replace n by 2, that gives you positive. N by 2, so that gives you 2 to the 4th, which is 16. X to the 6. Okay, that's I replace the n by 0, 1, 2. If I replace it by 2, so 2 to the 4th, which is going to be 16. And that would be 6 and divided by 4 factorial. And then you just continue. So that condensed form is much easier to get these type of ideas. Okay, so this is the way we are going to operate for these nice functions. But sometimes you may be, given the order and asked to do it, find, a couple of terms of the Taylor series, for example. So give you another one. So be ready for different sort of problems. Okay, this is another type. And you cannot use any shortcut for this one. Okay, you are going to be asked to find the first 4 terms. 4 terms of the Maclaurin series of the, okay, Maclaurin series for this function of the function f of x equal to the, let's say, a radical. Okay, you can have 1 over, if you like, radical x plus 1. You see, it's not of the form of e to the x or those type that we talk about it. So you have to do it. That's why they ask for the 4 terms only. Okay, it's a Maclaurin series, and the Maclaurin series in terms of the 0. So this is what you have to do. You see, there's no shortcut for this one. You just write down what you want to do. Okay, the first 4 terms of the Maclaurin series would be, you see, that's it. So you can say the f of x is going to be, it's a Maclaurin series. You can use this notation if you like. So the first term is going to be f of 0. Then f prime of 0 times x. F double prime of 0 times x squared divided by 2 factorial. And f to the 3rd at 0 divided by 3 factorial x to the third. You see, 1, 2, 3, 4. So you have to find these fourth coefficients yourself to be able to answer the question. So patiently evaluate it. This is it. This is your f of x. So you find f of 0 first. Okay, this f of x. So this is it. This is my f of x. I write it down here again. 1 over radical x plus 1. If you want to differentiate it, you have to move it up. You know that's going to be x plus 1 to the negative half. So make it ready. Okay, so if you want to find the f of 0, that's easy. You substitute 1 square root of 0 plus 1, which is going to be 1, because 1 over radical 1 would be 1. So f of 0 would be 1. So that's the first coefficient. We need the second one. You have to differentiate it first. This is it. This is your function. Differentiate it. So what's going to be f prime of x? Use the chain rule. Bring the negative half down. Remember, x plus 1 to the 1 down. Negative 1 minus 1 would be negative 3 half. U prime is 0. Then you are going to find it at 0. So f prime at 0 is negative half. You see, the bottom one would be 0 plus 1. You see, 0 plus 1 to the negative 3 half. That would be 1. Because 0 plus 1 would be 1. 1 raised to any power would be 1. So that gives a negative half. So f prime of 0 would be negative half. You see, that's your second term. Okay, you have to continue to get the next one. So what's going to be the next one? And this is going to be f prime. You differentiate it again, f double prime, another chain rule. It's going to be, you bring the power down, so it's a negative half already. It's going to be negative 3 half times x plus 1 to the negative 3 half minus 1. It's a negative 3 minus 2, negative 5 half. Negative 5 half. So that gives you negative 3/4. 3 times 1, 3, 2 times 2, 4. 3/4 x plus 1 to the negative 5 half. If you substitute for 0, you see this is going to be 0 plus 1, which is 1. So that gives a negative 3/4. Negative 3/4. I write it down for you. It's going to be 0 plus 1 to the negative 5 half. But the second part is just 1. So that gives a negative 3/4. So f double prime of 0 is going to be negative 3/4. Okay, where we are here. One more to go because they asked for the first. Okay, so it's not difficult, but you got to be patient to find it. So let's see. This is f double prime. You have to differentiate this one once more to get the FTRs or the third derivative. So we go to the next page. So I take it from here. We have the f double prime of x is equal to the what? Is equal to the negative 3/4 x plus 1, negative 3/4 x plus 1 to the negative 5 half. So we differentiate it again. So we get the FTRs, the third derivative at x equal to, that's a negative 3/4. You bring the negative 5 half down. That gives you x plus 1. Negative 5 half minus 1. That gives you negative 7 half. Now you multiply negative positive, so that gives you 15/8. 15/8 x plus 1 to the negative 7 half. So you find it at 0. You see, you get this one at 0. So the result would be what? The result would be 15/8. 15/8. As you can see, these numbers, getting different, complicated as we go on. But they asked for the first 4 terms, and now we are ready. So this is going to be the solution. You said that the function was f of x, and they ask for, I write it down again. So the first term, the second, the third, f double prime 2 factorial, x squared, and the fourth. That is going to be the fourth. Now substitute. Remember, I remind you, f of 0 was 1. F prime of 0, we find f prime of 0 is a negative half. So that's a negative half. Okay, and f double prime of 0. F double prime of 0 was a negative 3/4. And the f tiers, or the third, 15/8. Okay, substitute here, simplify, then you're done. So the 4 first term of the Maclaurin series of the function are going to be of the following. F of 0 is 1, 1. F prime of 0, negative half, minus half of x. Okay, f double prime of 0 plus f double prime negative 3/4, and you have a 2 factorial over here. Okay, 2 factorial x squared. Next one, plus f tiers is a 15/8 over 3 factorial x to the third, etc. So this is it. 1 minus 1/2 x. You can simplify this one. You can bring it down. So it's going to be minus 3 on the top, 4 times 2 factorial down the bottom, x squared. And this is going to be 15 on the top, 8 times 3 factorial, x to the third. Okay, so eventually this is your function, the Maclaurin, or you can write, you see that's it, that's a given one, 1 over radical x plus 1. It would be eventually equal to, this is going to be 1 minus 1/2 x. Okay, 1/2 x is going to be minus 3 on the top, 2 factorial is 2, 2 times 4, 8, 8x squared. And the next one is a positive, it's going to be 15. 3 factorial would be 6, 6 times 8, 48. X to the third, going on forever. Okay, so this is going to be, just checking this f prime of 0. That's a negative 3/4. Okay, f double prime is negative 3/4, negative, positive, negative, and that was positive, yes. So this is it. You see, it's going to be 1, 2, 3, 4 terms of the. Sometimes there is a nice pattern, then you can guess what is going to be the next one and going on forever, and sometimes it's not. So we may ask you to just give us the 4 terms, and that would be the 4 terms in these cases. That's it. You see, very nice one. The Taylor series and the Maclaurin series. Just knowing the theorem is not going to be useful. You see, these tricks that I gave you, be able to apply it. This is going to be the one. So we are almost done with all the power series that we need. So I'll post another recording for you. It's kind of application and going on some problems, and then I will post the practice quiz and the quiz for you. Your last quiz, number 4, and you set up the time for the next week, and then what we are going to do, we may give you a little bit of the polar coordinates. Okay, just as long as we have enough time. So you just get something out of it in case you want to take calculus 3, that would be useful for you. Okay, they have to explain it in calculus 3, but it's not bad. So we try to give you a little bit of that one too. Okay, so that's it. Study this one carefully. These methods are very important. Okay, and you can also read your book. So when I post the quiz, you will find out which type of question we are interested in. I post the practice quiz, then I give you the solution of that practice quiz, okay, to just make sure you are ready for it. And everything you do on this quiz, of course, will be repeated for the final exam that we're going to have. Okay, and I try to take care of your test to make sure that we are almost done. And so the last time that we did calculus 2, we didn't get time. Even we didn't get time to talk about this, before during that pandemic. It's good now we get somewhere over here. Okay, so don't worry. If you need anything, email me. And take care. Bye-bye.